All right, so circuits is what we're talking about today for our AP Physics 2 review. Um, you want to keep a couple things in mind when you're going with circuits, a couple main formulas that you want to be thinking about that you would have experimented with in classes. Ohm's law, V equals IR, and then power equals IV, and these solve most general R resistor-based circuits. We'll also get into a little bit with RC circuits for the context of AP Physics 2. Ohm's law relates to voltage. That's your input. Your pushing power, if you will, for the charges to move through. Current is the rate at which charges move through the circuit, and then resistance is how easy or difficult it is to move through the circuit. So we're going to first talk about resistance and what controls that, manipulates that. There was a AP Physics 1 problem from a couple years ago that gets everybody riled up about this. It was resistivity associated with this, and they used conductive dough. So we want to think about, we have some dough that is short, and then we have some dough that is a little bit wider, so thin. And then you think about what would be easier for charges to manipulate or meander through this. And we can look at some differences that are associated with it. Let me make this one a little bit longer. So the difference between these two right now is simply their surface area of the end. I talk about driving through a mountain, and I'd rather drive through a tunnel that is large than a tunnel that is small. So when you think about the two variables that you can measure here, you would be measuring the surface area. So notice that I've kept the length of the two relatively close, but we would say that the wider the surface area, the larger the path for the circuit, the charges to flow through, the less resistance it has. So we start building a formula by saying that the resistance is inversely proportional to the surface area. So now we would just we've manipulated that. We changed one variable at a time, so we've taken care of that. So now we're just going to look at this other variable. We'll look at just the smaller of the two, the narrower of the two. And we manipulate one other variable, and that other variable is the length of the wire. Which one of these would be easier to transverse through, to manipulate through, to meander through, however you want to think about it. The longer the wire, the more challenging it would be, the longer it would take for something to get through it. The shorter it is, the easier it is to get through it, so, or less resistance. And we find that to be the length of it. Ultimately, what we're doing is we're describing the resistance of a wire dependent upon the length of the wire and the surface area of the wire, the cross-sectional area. But there's one other factor that plays a role. It depends on the material that it is in, and we want to be aware that we have the resistivity, which in this case is rho in your formula chart, and it's a constant for each different material. Spelling is hard. Okay, so we've got the resistance formula, and usually you would describe this comparative analysis, which one's going to be the most resistive material, which one's going to be the least resistive material, and why, and you would want to reference this and talk about the direct relationships and the inverse relationships. If you had to do any calculations, you probably want to be aware of the cross-sectional area of a cylinder, which would just be the area of a circle, pi r squared. So just some basic geometry and shapes associated with that. That's the end of that idea. Then you move on to what a circuit is, and you have an input voltage. You have something for the circuit to go through, and a wire connecting the positive end, the long end, to the negative end of the power supply. In this case, I like to think of it as a battery. So we just call it, we give it a voltage, and then we have a resistance. Current in AP Physics 2 uses the conventional flow of current, which means that the current would flow from the positive end of the battery to the negative end. You'd go from high potential to low potential. But what is required is it takes energy to get through this resistor. And depending on the resistance of the resistor, determined down here, the amount of energy that would be needed would be used. So how do we determine how to start figuring those things out? Well, we start using in this case, the loop rule. And the loop rule is how you'd solve most circuit problems, and you'd also use the junction rule. What the loop rule says is that the input voltage added with all of the losses of voltage will always equal 0 for a closed loop circuit. So I like to think about it like this, where we have an input voltage, there will be some voltage in this resistor, and when I combine those two values, it'd be 0. So I like to think of V input minus V in that R in this case equals 0. So that's how we can figure out, in this case, how much voltage is located right there. And then we can also then begin to think about, well, how could we figure out current? And we know the voltage, we know the resistance, and we can solve for the current. In addition, we could determine the amount of power that's in this circuit, because we now know the current and the voltage. I equals V over R. But we're going to be using the loop rule quite a bit. We also use the junction rule. But that's just a conservation of charge concept. Loop rule is a conservation of energy concept. I've drawn now a series circuit with two resistors. We call this one R1, and we'll call this R2. We need to start thinking about what we would find in what we could find in all of this problem. A basic problem just to get us started at remembering how to do all these other problems. But we would have to identify what the total resistance of this is. And to get the total resistance of a series circuit, we just take the sum of the R. So in this case, it's R1 plus R2. What we'd be aware of is the ratio of these two voltages would depend on their resistances. The higher the resistance, the more voltage it would be required, or the more energy required to get through it per unit charge. So we can look at some ratios. I have some students that like to look at ratios, but you could also just say the voltage here plus the voltage here equals the voltage here, which is from our loop rule statement. We could say that the voltage input is equal to the voltage in R1, which plus the voltage in R2. That's a loop rule statement. What we have in minus what we lose equals 0. I just moved those over. So to prove what's going on in this statement, they say that the sum of the voltage equals the total voltage, but the sum of the resistance equals the total resistance. What we find in a series circuit is the current is constant throughout. And that's a huge feature that you need to remember while you're taking your AP exam. In series circuits, the current is constant throughout. With that being said, I could derive this formula. It's on your formula chart. It'll be there for you to keep in mind. So I'm not going to spend the time deriving that statement right now. So I say the current is the same throughout. And then you could say V divided by R plus R is the statement that you'd be looking for if I wanted to find the total amount of current. I could say the total voltage VT, which is here, the input, divided by the sum of the resistance, the total resistance, which in this case is R1 plus R2. And now you found the current in this circuit. A common technique that a lot of students use, it's not something that the College Board would ever ask you to use or to necessarily show, but it's a nice tool, a crutch, if you want to think about it, is a VERC chart. So I don't have a ton of room here, but you can still see that VERC chart. And then you'd have your inputs. I'll call it BAT. And then you have the resistor 1, resistor 2. So we could think of a couple bits of numbers here if you want, just to solve it out nicely. We can do a 6-volt battery with a 1 ohm resistor and a 2 ohm resistor to see some of the relationships that we find with it. This isn't the most effective way to do it, but in the shortened amount of time that we have, I think it does the job. So I know that there's an input voltage of 6. I know that the resistance of R1 is 1, and I know that the resistance of R2 is 2. It becomes somewhat of a predictable Sudoku puzzle. You don't have to do a lot of guessing. I know that you don't have to guess in Sudoku if you do it correctly. But we then fill in what we can, and what we can say is the amount of resistance for the total circuit would just be 1 plus 2, which is 3. So we have 3 volts. We then use the current statement to say I equals V over R. So I equals V divided by R. We find this to be 2. Because it's a series circuit, and a property of series circuits is the current is constant throughout, we find that the current is 2 everywhere. And then what we allow us to do is then confirm what the voltage is, 2 volts, 4 volts. And you can see that the higher the resistance, it's twice as much resistance. It requires twice as much voltage to get through for a series circuit. We'll look at a parallel circuit here shortly. In terms of this, we see that 2 plus 4 is 6, so we feel like we've done something correct. And then our last check is what power is. Power is IV. So we do IV 12, 4, and 8. So the total amount of power consumed, energy per unit time, is 12. And 4 plus 8 is 12. So that says the energy in is the energy used. So that's something good to keep in mind. Some asides associated with power as I got through that problem that you might need to use to save you a little bit of time is if I know that P equals IV and V equals IR, then I can say that this must equal I times IR. I substituted this V with that V, and I can say that that is equal to I squared R. In addition, for that being I squared R, I can make a substitution with the I and say that I equals V over R from my Ohm's law statement. Substituting that in, I can also say that we have V over R times V equals V squared over R. So that's something to keep in mind while you're using your power statement. So we have Ohm's law and power, incredibly useful tools to solve these problems. Parallel circuits are a little bit different, but we're going to use the loop rule to help us solve it, but then we're also going to use the junction rule. Parallel means it has multiple branches and multiple paths for the current to flow. So I have my parallel circuit right there. And then what I'm going to do is draw 2 separate loops. I'll have a green loop, this first, going from the positive end of the battery to the negative end of the battery. But then I'll also have a red loop, because it needs to complete the cycle. It goes from positive to negative. It doesn't ever go from high to medium, back to high, down to low. It just goes from high to low. There's another loop. So you see that we have 2 loops, which means we have 2 loop rules that we could write. So we got the voltage input minus this voltage in this resistor. We'll call this R. We'll call this one right up here. We'll call this just RT. And we'll call this, that's a V. My apologies. Call this RT. No, T is not a good choice. R1. Call this other one R2. Okay, so we have our V input minus the voltage in R1. Equals 0. And then we also have a statement that says the same voltage input minus the voltage in R2 equals 0. And now we've used 2 loop rules, which means we can start writing 2. We have the ability to know less because we have more statements that we can write that are true. What this ultimately tells us is the amount of voltage in R1 is equivalent to the voltage that is supplied by the battery. But it also says that the amount of voltage in R2 is the same amount as the voltage in the battery. So the voltage here is equivalent to the voltage here is equivalent to the voltage here. If this is 3 volts, this is 3 volts, and this is 3 volts. Some students get this confused with their series circuits, where they would want to say that since this is 3 volts, that this plus this better equal 3 volts, but that's not correctly using the loop rule. That's an incorrect technique. It'll get you incorrect answers where they'll say that this is 3 volts. They'll say that this is 1.5 volts, and they'll say that this is 1.5 volts. And they'll feel good about it because 1.5 plus 1.5 equals 3, but they are incorrect. There's one more statement, the fact that we can write about this. And I basically drew the path of a charge. And you might see that the red and green overlap in a few different places. All right, so we have right here, that's where red and green overlap. Red and green also overlap here, but we see that we only have green across the middle and we only have red across the top. But over here we have both of them. So there is more charges moving through these two blue areas than there is in those two areas. But the amount of blue that's here either goes this way or it goes that way. So there's an or aspect of a parallel circuit. So the current either goes through R2 or through R1, but when it gets back to the other side, the current that went through R1 recombines with the current in R2, and we're ready to describe the junction rule. The amount of charge that is located here is also located here or here, but we need to add them. So I say that I have like this blue current, which is in this case the total amount of current, and that is equal to, this is the junction rule, the current in R2 plus the current in R1. And this is a junction rule concept, conservation of charge. The amount of charge that's here is equal to the amount of charge that's distributed through the junction. In this case, there's one junction, so we need to do one addition statement. This ultimately helps you solve and justify why all complex problems work out the way that they do. But we want to think about a couple things that we're away to take away from here is that the current is an additive statement, but the voltage is the same in both, in this case, branches. So working with a colleague, and over time have come up with this really stupid way. Notice that if you're really dumb about it, you can make the L's look like a V for a parallel circuit. So that's the basic idea of what a parallel circuit is. Again, energy is conserved, and the charge is conserved. So we have junction. I'll write junction over here. These are Kirchhoff's laws, and sometimes they refer to like tell students to using the Kirchhoff's laws, loop rule and junction rule, justify your answer. So you should make sure you are aware that this is Kirchhoff's. I probably spell it wrong all the time. I don't know. Let's try this today. Kirchhoff. Keep that in mind when you're solving the problem. What you find is as I add more resistors in parallel, the overall resistance of this decreases because I've given the charges more paths to go through. So we don't see this additive approach of resistors in parallel. We find an inverse action, which leads to a couple of challenges that students have when using a calculator, which is something that you'll need to make sure you have access to while you take your AP exam. But for resistors in parallel, the formula chart tells us a statement that looks like this. Ooh, it's just like the sum of 1 over R. Actually, it says it like this, 1 over RP. The RP stands for resistors in parallel, and this is R for all the resistors that you'd have. If I were to write this out, I like to write it out like this, where I take the resistance, and then I say, well, that must be equivalent to 1 over R1 plus 1 over R2. In our case, we only had 2 resistors, but notice that I inverted this side to make it that. So I must also invert the other side. So keep that in mind when you're solving these problems. The total amount of resistance in a parallel circuit is less than an individual resistor. So it's a wild concept. If you add resistors in parallel, the overall resistance goes down. But when you go out Black Friday shopping, it would be atrocious if they had one cash register open to check out. So what they do is they open as many as possible, and that allows the current of traffic inside of the store to move more quickly. So adding resistors makes the overall resistance go down if you add them in parallel. All right. I guess we could go through a basic calculation. Let me think of some numbers. Okay, if I do 4 ohm resistor here and I do a 12 ohm resistor here, I think we'll be okay. Yeah, let's make this 9 volts. Again, just to show some of those relationships we just talked about, we can see it in numerically, although I think the College Board's not going to ask you a tremendous amount of numerics. Total resistance, our total voltage was 9. We have a resistance of 4 and we have a resistance of 12. So I have to find this as R1. I have to find that as R2 in this orientation. It doesn't make a difference. What we can say is that the parallel, so these all are 9 volts. Yeah, it works out not the best, 2.25 3/4. But a couple of different ways you could solve this out is you could just do your I equals V over R, and you find this to be 2.25, and you find this to be 0.75. And then we say for junction rule, we would say that because of the junction rule, the current that's here must be equivalent to the current here plus here, and we find this to be 3. As a result, we find the total resistance to be 3, which should be a little off-putting because this has a resistance of 4 and this has a resistance of 12, but the overall resistance is less. So when we do the math, we see that we have 1 over R plus 1 over the other R, and we take it to the -1. Without access to a calculator, I need to find the common denominator of these two statements. I find the common denominator of these two statements to be 12. So I get 3 over 12, which is 1/4, plus 1 over 12, which is 1/12, and I get 4/12. When I invert all of these, 12 over 4 is 3, and I find that I did it okay. By adding an extra path, we reduce the total resistance. I don't know what I want to do here. 27, 18, and 9/4. I'll get a calculator. 20.25. And I knew that. 6.75. 6.75 plus 20.25 is 27. So you find the conservation of power and energy there as well. We use loop rule to find these 9s. We use junction rule to do this. We use Ohm's law to fill in as much as you could, and then you let the rest take over. I showed you an alternate way to find the total resistance, which allowed you to find the total current. But that's your introduction to basic circuits, parallel, and series. You can get into complex ideas. I anticipate that what they're going to ask you about complex ideas is what happens if I do this to the circuit. But let's just take a look at a complex circuit and see what we think. So try to draw these as different as I can, but I always end up drawing them very similarly. You should be ready for a lot of different pictures, and I'll show you some of those in practice problems. We need to immediately identify this as not a series, a simple circuit, but a complex circuit, because we see a series component and we see a parallel component. I go through this one, and then I either go down or I go up through this one. So you could draw lots of different loops. One loop that you could draw is I could go this path through the circuit, but there's another path that I could go. I could go through the top branch of my parallel, and you see that you have a total current here, you have a splitting of the current here. You see that all the current goes through series, so that helps you identify that this is a series resistor. You can see that it splits here, so that helps you identify that those are parallel resistors. And then what you can do is begin to, think about how you could do it. You can manipulate a few things, but what you want to be aware of is where's the most current. Rank the currents. So the current is the most through the series circuit because it gets all the current. That's just by definition. All of the current goes through a series resistor. In addition, what you would then do is identify which one of these had more resistance. The one that has more resistance has less current. There's an inverse relationship between I and R. Justification comes from Ohm's law. As resistance goes up, current goes down. I'm able to keep this V constant because the voltage in both of these is the same. That's because of the loop rule to keep in mind. Parallel branches receive the same amount of voltage. In this case, they receive whatever remains after this is removed from the total battery. So if there are 3 volts here and this was 9 volts, then this would get 6 volts and 6 volts. That's unlikely, but it's a possibility. So keep that in mind, that this would get 3 volts and this would get 6 volts and that would get 6 volts. That's the impossibility. Not that this would get 3 and these would both get 6 to be 9. So you keep going on with that, and then you could rank them. What would happen to the current here if I remove this resistor? If I get rid of this, then all of the current would go through here and all of the current would go through here. However, the total resistance of the circuit would go up because I removed a parallel branch. So since this resistor is gone, the total resistance has gone up, which means there's less current here, but now all of the current would be going through that one. So this current would go down and this current would go up if this resistor were removed out of the circuit. So you want to employ a lot of different techniques associated with Ohm's law and then your loop rule and junction rule concepts. I realized that I wanted to make sure I talked about a voltmeter and an ammeter as well. So I'll show you appropriate placement of a voltmeter. A voltmeter should be identifying the voltage in a resistor. And in order to measure the voltage appropriately, you want to make sure you put it in parallel. So keep that in mind. Voltage is the same in parallel branches of a circuit. So when you're measuring voltage, make sure you're measuring it in parallel. That's a voltmeter. We used multimeters in classes and set it to read voltage. If I want to measure current, we identified a long time earlier today that the current is the same in series. So I want to measure current. I want to put my ammeter, my device that measures current, directly in series with where I want to know. So if I wanted to know the current right here, I could identify that by putting an ammeter right there. So an ammeter, you want to be in series, and a voltmeter, I don't know, maybe voltometer, I don't know, just call it voltmeter, measured in parallel. So some things to keep in mind there. All right, last thing I wanted to talk about today with circuits is you only have to deal with this in steady state terms, but they like to think about what would a capacitor do. So if I plug in this new device of a capacitor, I have an RC circuit. It's complex, but we need to think about what a capacitor does. A capacitor stores charge. That's all it does. And what happens is current flows through to it for a while. And in a calculus-based course, you figure out the rate at which current flows to it with a differential equation. However, in an algebra-based physics class, you don't have to worry about it. What you have to be aware of is initially, there are no volts located in it. Why are there no volts located in it? Because no current has had a chance to get there yet. So initially, the voltage in the capacitor, in the capacitor at time equals 0 is 0. However, after a long period of time, the amount of voltage in this would be equivalent to the amount of voltage that is located here. And to figure out the amount of voltage located here, after a long period of time, at time infinity, the amount of current that goes through here would actually approach zero. So it would receive a lot of current, but after a long period of time, it would receive no current because it'd be full. There'd be no value in going this way. It's a gap in parallel plates or some storage mechanic. So ultimately, we look at this being in series, these two resistors being in series, and these two being in parallel. And since they are in parallel, they have the same voltage. So the voltage in the capacitor at time equals infinity would be equivalent to the voltage in this, we'll call it R2. To get the voltage in R2, you just say V equals I for our loop rule divided by R1 plus R2. Now you know your current, and then do V equals IR, and you got yourself the voltage here, which means you have yourself the voltage here. What this also means is at time 0, the voltage in R2 is also 0 because these are in parallel, which means all of the voltage initially is located here. You look at some things in AP Physics E, it's a natural log statement, logarithmic scale, where you look at the rate at which it happens, but we only need to worry about initial and final states. And that's a brief on capacitors. Thanks for your time. Circuits. Have a great day.